Now let's analyze the Exergy balance for a steady flow system. So for this analysis, let us consider a control volume through which some steady flow is happening. So there are two sections to it. So this is section 1, this is section 2. This is the control surface of the control volume, and the boundary temperature is T sigma. Through the boundary, some heat transfer is taking place Q12 because the process is from 1 to state 2. There is some work output in going from state 1 to state 2. Now, because it's a steady flow process, some mass flow also happens. So let us say at inlet the mass flow is m1 and at the outlet the mass flow is m2. So let us apply the first law and second law on this control volume, which is having some flow through it. So let's first of all apply the first law. Now if you apply the first law, it will come, and let's apply the steady flow energy equation. So let's apply the steady flow energy equation onto this control volume, and that would be H1 plus m1 v1 square. So let's keep it to be the same for the moment. mv1 square plus mg z1 plus q12 is equal to h2 plus mv2 square by 2 plus mg z2 plus w12. So this is what you get after you apply the first law onto this particular system. Now let's apply the second law. Let's apply the second law onto this. Now when you apply second law, you get S1 plus integral state 1 to state 2 dq upon t minus S2 plus, not plus, equal to, this would be the entropy which is generated in the system. Okay, so when you multiply this equation by T naught, let's multiply it by T naught. So we would get T naught into S1 minus S2 plus T naught into integral 1 to 2 dq upon t is equal to T naught into the entropy generation. Now T naught into entropy generation is your irreversibility, that is capital I. Now let's consider this equation. Let us say this equation is equation 1 and this equation is equation 2. So let's combine these equations. So let us first of all rearrange equation 1. So when you rearrange equation 1, let's have a look at it once more. So it's a basic steady flow energy equation. So upon rearranging equation 1, we would get H2 minus H1, okay, and then you subtract this part or this equation from that. So you would have minus T naught into S2 minus S1. Then you can combine the velocity heads. So you'll have v2 square by 2 minus v1 square whole upon 2, and then you can combine the potential heads, mg into z2 minus z1. Okay, so let's take this on the right hand side and let's keep the work on the right hand side as well. So we would get equal to, so we'll bring this particular term on the right hand side. So we'll get the value as dq. Now for the whole process, this is going from 1 to 2, isn't it? So if you talk about this can be written as, this can be put as integral 1 to 2 dq. It is same as q1 to 2. So this is, now you can bring this to the other side, you'll get minus T naught upon T integral 1 to 2 dq. Alright, and you'll have minus w12 minus the irreversibility. So this is an equation that will come after combining equation 1 and equation 2. Alright, now let's move a bit forward. Now if you combine these two terms, alright, and if you look at it, it will become integral 1 to 2 brackets 1 minus T naught upon T sigma. So let's put T sigma over here because it's the boundary temperature, dq minus work in going from 1 to 2 minus the irreversibility. Alright. Now if you look at the left hand side of this particular equation, this complete left hand side is the difference in the availability. So it will become A2 minus A1 is equal to integral 1 to 2 1 minus T naught upon T sigma into dq minus work 1 to 2 minus infinity. So this is the equation that you get. That is the difference in the availabilities. Now if you try and make it in the form of a rate of change, or you want to get a rate equation, so the rate equation would become, let's start with this. So this integral would be replaced by a summation sign, 1 minus T naught upon T, okay, into Q dot, that represents the rate of flow of heat, minus the work transfer rate from the control volume, plus m dot, that is the mass flow rate, into AF1 minus AF2. Now what are these AF1 and AF2? Let's talk about that. Minus the rate of irreversibility through the control volume, and that is equal to 0. Now this particular term, this is worth noting it down. So because if you look at multiply with the mass, you get the complete value, but if you only take this value, this is per unit mass. So AF1 minus AF2, this is equal to H1 minus H2, that is the per unit mass enthalpy, minus T naught into S1 minus S2 plus V1 square minus V2 square by 2 plus G into Z1 minus Z2. So this complete term is your AF1 minus AF2. Okay. Now if you bring this particular equation down, and let us analyze this equation for a single stream which is entering and leaving. Okay, so for a single stream entering and leaving. Alright, so for this particular case, let's divide this whole equation by m dot. So you'll get, and for a single stream you will be getting rid of this summation sign as well. So you will get 1 minus T naught upon T into Q dot, and let's divide the whole equation by m dot, minus W dot by m dot, okay, plus AF1 minus AF2, and let's take this towards the right hand side, and you will get I dot upon m dot. So this is what you get. Alright, now if you combine, or if you look at these terms one by one, there is one term in the shape of this particular term. The other term is a combination of these terms, and the last term is this particular term. So this is the term which says the inlet exergy. So this is exergy in, and this is exergy out, and this is exergy destroyed or exergy loss. Okay, so this is how you can analyze the exergy balance for a steady flow process. So I hope you understood the analysis that is represented over here. Now after this analysis, let us look at some illustrations of second law efficiencies.